Thank you for joining me today. In this lesson, we are going to be talking about chemical formulas, specifically empirical and molecular formulas. So empirical, this is a word that you're probably not familiar with. We don't really use it that much in common, normal, everyday talk. But what the word empirical simply means is determined through measurement, observation, or experiment. So when we call something an empirical formula, what we're saying is that it is the formula that is determined through experimentation. And that's done, when you do that, you end up with the formula with the smallest ratio of elements in a compound. As we learned in the last lesson about percent composition and that law of definite proportions, that they have a specific proportion. The issue is there's some compounds that may have similar proportions, but they're going to have different actual molecular formulas. So it's generally determined, the empirical formula is generally determined through data analysis and through experimentation. Now, percent comp is unique to a given compound, but many compounds can have the same empirical formula. And that happens because they have multiples of the same thing. So for example, we have C4H12 and C3H9. Both of these have the same empirical formula. They are different molecular formulas. C4H12 is a different compound than C3H9, but the empirical formula is the smallest possible ratio of elements in the compound. So C4H12, 4 and 12 can both be divided by 4, and 3 and 9 can both be divided by 3. So you can reduce the subscripts for both of those and end up with CH3 both times. So even though they are different compounds, they have the same empirical formula. They'll have different molecular formulas, but the same empirical formula. So there is a way to distinguish and figure out what the molecular formula is from the empirical formula, and we'll get to that in a minute. But how do we determine the empirical formula first? What's the first thing we need to do? So experimental data is used to determine that empirical formula, usually by experimentally measuring the percent composition. Okay, so we end up with a compound that we don't know what it is. We run it through a device called a mass spectrometer, and it's going to separate it out, and you're going to be able to figure out the mass of the elements that make it up. All right, and once you know what the percent composition is, we can use that percent composition to figure out what the element is. And when you don't know, we measure its percent composition, and then we use that to determine the empirical formula. The steps to find the empirical formula are not that complicated. So we're going to first assume that you have 100 grams of a compound. We do that because our percents make it a whole lot easier. If I have 100 grams of a sample, then if it's 33% oxygen, that means I have 33 grams of oxygen. That's pretty simple. So we're always going to assume that we have 100 grams of our sample. And then we're going to convert all of those amounts to moles. That's why we spent that time doing mole conversions, because we're going to convert our grams to moles so that we have a molar amount. And then we're going to divide all of those by the smallest number. It's because we want a ratio of things together. So we're going to divide by the smallest number. You'll see this in the example. Now, if you end up with decimal answers after you divide, then you have to multiply to get whole numbers. So what I mean by this is it's going to take some practice, but what I mean is you need to be familiar with some standard fractions. So if you end up with something that's like 1.5, well, 0.5 is the fraction of 1/2. So you know that you've got a half of something somewhere. So we're going to multiply everything by 2 to get rid of that fraction. So you need to be familiar with those standard fractions, like a half and a third and a fourth. So 1/2 is 0.5. So if you end up with 0.5, you know you're going to be multiplying things by 2. If you end up with 0.333, you know that that's 1/3, so you're going to multiply everything by 3. If you end up with 0.25, that's 1/4, so you're going to multiply everything by 4. So you have to be familiar with those standard fractions. Sometimes it's going to be really close to a whole number, like you'll have 1.999, and then you just round it up to 2. And so that's okay. But for the most part, you're going to end up with whole numbers after you do this fourth step, after you have multiplied things together, you should end up with whole numbers. And those whole numbers become the subscripts for your empirical formula. So let's look at an example of how we do that. Let's say we have methyl acetate. Now we know it's methyl acetate here, but you're not always going to know what it is. So let's say we have methyl acetate is made up of 48.6% carbon, 8.16% hydrogen, and 43.20% oxygen. So I have carbon, I have hydrogen, and I have oxygen. Now, it tells us that we have 48.64%, and I'm going to pretend my percentages are grams. So I have 48.64 grams of carbon, and so I have 8.16 grams of hydrogen, and I have 43.20 grams of oxygen. So I'm going to assume I have 100 grams of sample, and then I'm going to have that many grams of each element. So now what I need to do is convert each of these into moles. So I'm going to do my railroad track. If I have grams, I'm going to put the molar mass on the bottom. So that's 12.011 grams of carbon and 1.008 grams of hydrogen and 15.999 grams of oxygen. Those are the molar masses of these elements. And this is going to be 1 mole of carbon, and that's 1 mole of hydrogen and 1 mole of oxygen. So when I do this division, I have 48.64 divided by 12.011, and that's going to give me 4.0496. I'm not going to write down all of the digits, and I'm not going to worry about rounding it off to significant figures just yet. So my next one, I do this one, gives me 8.0952, and doing this division gives me 2.7002. Now, the next thing we do, once we've converted them all to moles, we need to divide by the smallest. Well, 2.7, 8.0, 4.0. 2.7 is the smallest, so I'm going to divide by 2.7002 for all three of them. All right, so obviously 2.7002 divided by itself is 1. That's the thing, you're always going to end up with 1 of some of them because we're looking for the ratio of the elements. That's the whole point, is the empirical formula has the smallest ratio. So we're going to find the ratio, so that's why we divide by the smallest, because it will make one of them always be 1. Okay, so when I do this division, that gives me an answer of 3. And when I do this division, it gives me an answer of 1.5. Well, it's actually 1.499, but I rounded that to 1.5. And remember, 0.5 is a fraction of 1/2. So I need to get rid of that fraction. So I'm going to multiply by 2. So I multiply by 2, giving me 3 for that one. But if I multiply that one by 2, since I have to keep the same ratio, I have to multiply all of them by 2. And so I end up with 3, 6, and 2. So what this tells me is these are the subscripts in my empirical formula. So that means I have carbon, hydrogen, and oxygen in my formula, and my subscripts are 3, 6, and 2. And this is my empirical formula for methyl acetate. Now, if you look it up, you'll find that that actually is also the molecular formula, and oftentimes the molecular formula and the empirical formula are the same, but not always. So, what is a molecular formula? Well, a molecular formula is the actual formula for the compound. Sometimes when we find the smallest ratio, we get the actual formula, but not always. Sometimes that actual formula is a larger multiplied version of the smallest ratio. So sometimes the molecular formula and the empirical formula are the same, but not always. The actual formula of the compound. So the actual formula is already If the actual formula is already the smallest, then the molecular formula and the empirical formula are the same. Now, once you know the empirical formula, you can pretty much always determine the molecular formula quite easily. Finding the empirical formula is a little bit more difficult, but once you know the empirical formula, you can always find the molecular formula. And you simply do that by comparing the molar mass of the empirical formula with the molar mass of the actual compound. And that's something that you can measure. We can measure the actual molar mass of a compound in the lab using sophisticated equipment. So once we know the empirical formula, we can take the calculated molar mass of that empirical formula, and we can take the actual molar mass that we find in the lab, and we can multiply them or divide them and get the answer. So this is the equation. N is our multiplier. So N is the mass of the compound determined experimentally, so the actual mass of our compound divided by the molar mass of the empirical formula. So once we find the empirical formula, we find its mass, and we have the actual experimental value for the compound's mass, and then we divide them. And that gives us, usually is going to be an integer. It should be an integer, either 1 or 2 or 3 or 4 or some multiple. It's not going to be a fraction, and if you did things correctly, it should always be an integer. Now, because of rounding and stuff, it may not be exactly. You may get 1.997 or something like that. That would round to 2. But it's going to be really, really close to an integer. So let's look at some things you need to look for. Is if your n, once you calculate that, if n equals 1, then that means the masses are the same, and your empirical formula and your molecular formula are the same formula. That's a case where your empirical formula and molecular formula are the same. If n is greater than 1, you're going to have to multiply each subscript in the empirical formula by n to get your molecular formula. So let's look at an example. If the empirical formula for a compound is found experimentally to be C3H4O3, the experimental data also indicates that the molar mass of the compound is 176.124 grams per mole. What is the molecular formula for this compound? So the first thing that we're going to have to do is, if I have C3H4O3, I have to find, this is my empirical formula, I have to find the molar mass of this empirical formula. Well, carbon's mass is 12.011, and there are 3 of them. And I'm going to add hydrogen's mass of 1.008, and there are 4 of those. And then I'm going to add oxygen's mass of 15.999, and there are 3 of those. So I put this in my calculator, I multiply it all out, and I get 88.062. So this is the mass of my empirical formula. So to find n, I'm going to take the actual mass, which is given to me in the problem, is 176.24. My actual mass divided by the empirical formula's mass, 88.062. So I do 176.24 divided by 88.062, and I get an answer of 2. So that means my n is 2. So what I'm going to do is take my empirical formula, and I'm going to multiply the entire thing by 2, giving me C6, because 2 times 3 is 6, H, 8, and O6. So I multiply all of these subscripts by 2. That's what the n does, is it tells you what to multiply your subscripts by. So the molecular formula is C6H8O6. That's not super complicated. You just find the molar mass, which we've been doing for a little bit, and you divide a couple of things that are given to you in the problem. So let's look at another example. A compound containing hydrogen and oxygen is found to have an empirical formula of HO. If the data also shows that this compound has a mass of 34.014 grams per mole, what is its molecular formula? So, if I have an empirical formula of HO, then I'm going to find the mass of HO, which is 1.008, the mass of hydrogen, plus 15.999, the mass of oxygen, which is 17.007. That is my empirical formula's mass. I then am going to take my actual mass that is found in experiment, 34.014, and I'm going to divide by my empirical formula's mass, and that gives me an answer of 2 again. You'll find as you do this that they're often going to be 2, sometimes 3. So I have HO. Each of them have a subscript of 1, so I'm going to multiply those 1s by 2 to give me a molecular formula of H2O2, hydrogen peroxide. So that is the molecular formula for that one. Not, again, not super complicated. Now, for these examples, you're not always going to be asked to find the molecular formula. Sometimes you will be asked to find the empirical formula when you're given the molecular formula. So that's what we're going to do on this. We're going to determine the empirical formula for each of the following molecules. So if I'm given P4O10, so I have P4O10, well, 4 and 10 can both be divided by 2. And so I do that. I divide them both by 2. I get the smallest possible ratio, and that gives me P2O5. So P4O10 is the molecular formula. P2O5 is the empirical formula. So I simply divide out my subscripts. I reduce the subscripts. So on this one we have C2H4. Well, C2H4. These can both be divided by 2. So I can reduce them. And so that gives me CH2. Once I reduce them, I divide that by 2, divide that by 2. So my empirical formula is CH2. You see, the empirical formula is the smallest possible ratio. So if you know the molecular formula, you can always find the empirical formula simply by reducing the subscripts. The last one, we have Fe2O3. Well, in this case, 2 and 3 cannot be reduced, which means the empirical formula for Fe2O3 and the molecular formula are the same. They have the same formula. So that is empirical and molecular formulas. So hopefully you have seen now that the empirical formula can be kind of complicated, but it's a really important skill to be able to do, and it's an important task that chemists actually do. This is how they determine what a chemical actually is whenever they find it in a lab. So if you've ever watched any of those crime scene investigation shows where they collect a sample of something and they run it through a machine and then it calculates and tells them what the chemical is, this is what's actually happening. It breaks it down and gets the percent composition. Now the machine doesn't actually then tell them what it is. It gives them printouts, and then a chemist has to actually do some analysis, and that actually is used to find the percent composition, is used to get the molecular or empirical formula, and then the empirical formula is used to find the molecular formula, and then we know what the compound is. So that's why we do this, and that's the important part of where this is used. So thanks for watching, and have a day.